There's a whole set of ratios and proportions
Yes.
embedded in creation itself. And whether we're talking sacred scripture and prophecy, whether we're talking architecture, whether we're talking art, whether we're talking growing things, whether we're talking about the great temporal relationships, time cycles, we're going to find the same numbers, the same ratios at work. And then I show historic metrology, which is showing like the Egyptian remen, an Egyptian unit of linear measure analyzed by F.H. Griffith in 1892 and by William Flinders Petrie and A.E. Berriman, considered to be equal to 20 digits or 14.58 inches. A.E. Berriman, in his work Historical Metrology, refined the length of the remen to be 1.2165. So if you take this calculator, Danny,
Right.
put in 1.2165, now that'll be in feet. That's the length of the remen. So you can see that it's a little bit, now this is an ancient Egyptian unit of measurement.
The remen.
The remen. It's a little bit longer than our foot, right?
Right.
Okay, so now there was another unit of measurement used in Egypt called the royal cubit. It was discovered by Isaac Newton in his analysis of the dimensions of the King's Chamber of the Great Pyramid based upon the Survey of Greaves in 1637, which, in fact, I'm sure you were well aware of. Also mentioned in the writings of Herodotus in his description of the city of Babylon. With slight variations, the accepted length of the royal cubit is taken as 1.72 feet or 20.6265. Now put in 1.72.
Am I clearing out the 1.265?
No, leave that. Actually, okay, here's what you're going to divide by 1.72.
1.72.
Right?
Okay.
Now, you see there's a little 1 over X button?
Oh, no, I hit equals.
Okay, you got to hit equals.
Okay, let me try this again.
Okay, let's go back. Let's go back to this.
1.2.
Put in 14.58 inches.
Okay.
Okay.
Got it.
Now divide by 20.6265
Okay.
equals, what'd you get?
0.70685.
Okay, so now do you see the 1 over X? Because we're going to flip the ratio. The 1 over X button. It should be
It's a button. Got it. Let's see. 1 over X.
third row.
Yep, got it.
Column. Hit that button.
Okay.
What'd you get?
1.414711934.
Okay, 1.414 basically.
Yes.
All right. Now, right to the right of that button, you'll see X squared. Hit
Got
that
it.
button. What'd you get?
2.0014.
So what you're looking at is the square root of 2. So what you just did, Danny, was you showed that the ratio of the royal cubit, the remen to the royal cubit, so the Egyptians knew this. If they drew a square, which was 1 remen on the side, and you drew its diagonal, the diagonal was the royal cubit. So that exercise we just went through, if you draw a square and it's 1 remen, which is, as it says here, say 14.58 inches.
Okay.
Its diagonal is going to be the royal cubit. And that was the basis of their measuring system, was that dynamic relationship of a square and its diagonal. Now, the royal cubit was used, like I said, by Newton in his analysis of the King's Chamber. Of the King's Chamber. It's also the thickness of the socle.
That's right.
Yeah.
Yeah.
That the pyramid sits on. Well, then, if we jump forward, the Palestinian cubit, the knowledge of the Palestinian cubit survives in the writings of Epiphanius, a bishop of Constantia in Cyprus, who wrote a treatise on weights and measures in AD 392. It conforms to the cubit of the altar, as mentioned in Ezekiel 43:13. That is, the cubit and the hand's breadth. The Palestinian cubit is generally taken as 25.284. Put 25.284 in your calculator, and I'll do the same here, 25.284.
Got it.
Now we're going to divide that by the remen, which is 14.58, and hit equals. Now hit your X squared key.
3.
3. So it's the square root of 3. So in other words, you imagine this now. Now the Palestinian cubit is used roughly in Palestine area about 1,000 years after the royal cubit and Riemann are being used in Egypt. Picture now, you start with a Riemann, you draw a square. Take its diagonal, that gives you the royal cubit. Use that to get your root 2 rectangle and take its diagonal. That diagonal is now the Palestinian cubit.
Got it.
Got it?
Got it.
So now we've got the Roman pace, the origin of the Roman mile. Now, you know the mile comes from the pace, right? You know what a pace is?
That's just like a human walking?
A human walking. Now imagine if you're going to pace out, you've got a field and you want to know roughly how big it is. You don't have a measuring tape. You figure, it's about an acre, but I'm going to pace it out.
Yeah.
Well, if it's in the old days and you're a surveyor, a builder, an architect, you're going to know pretty precisely the length of your pace because that's a common way of determining land measure is you pace things out initially. Mm-hmm. We didn't have transits and builders, instruments back then. We used things like ropes and chains. And
back then, what are we talking about back then?
God, anywhere before, from a few 150, 200 years ago.
Okay.
All the way back.
Okay.
Pacing something out.
Okay.
How many paces? Now, if you're pacing something out, you know that you're going to quickly learn that it's much easier if you are counting every other step than every step, right? You don't count left, right, you go right, 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 and you count, say, every time your right foot hits the ground. Okay, now, if you do 1,000 of those, that was the origin of the mile.
We've been using the mile for that long?
Oh, mile goes back. You find the mile, think about this, 1,000 paces. So you had a Roman mile, which was 1,000 paces in Rome. Now think of the word mile and think of the word mill, which means 1,000.
1,000, that's right, millennium, yeah.
Yeah, like a millennium.
A
millimeter, 1,000th of a meter.
Ah, okay.
So that's the origin. The mile and the mill, it's 1,000. So the original meaning of the mile was 1,000 paces. Now, our mile, how many feet are in our mile, Danny? I'm holding you conspicuous before the entire world at this moment.
1,000.
1,000
feet?
I
don't know. Let me guess.
Somebody, do you have your ruler?
10,000?
That boy needs his wrists.
10,000?
Hey,
I failed algebra.
Delivering any of that.
Dan?
I will claim the metric system, unfortunately, as the basis for my education.
Okay. Oh, no. We can cut Ben some
small get out of jail
here.
card free.
Okay. Now this is
You got an excuse. I don't.
Our fathers and our grandfathers all knew this. I think certainly farmers and builders and people like that who lived close to the land knew that our mile is 5,280 feet.
Oh, okay.
Now, if you divide 5,280 feet by 1,000, you'll get the length of the pace upon which our mile that we use today is based, right? So 5,280 feet, divide that by 1,000. That means that each pace was
5.28.
5.28. Very good. Right. Yes. 5.28 feet. If you had your notebook there in class, I would be getting you to write that down.
5.28.
5.28. Okay, you got it. 5.28. Now you look at the Roman pace here, and it's equal to 4.86 feet.
So they were shorter.
Yeah. You got it. Now our mile is part of the imperial system that goes back to ancient Britain. Now, I've looked at the surveys of Stonehenge, for example, and if you take the big outer ring of sarsen stone circles, within a few inches, it's 105.6 feet in diameter, right? And if you look at the sarsen stone uprights, which are the big stones forming that outer circle, that ring, there are lintels on top. Mm-hmm. And those lintels are an average length of 10.56 feet. 10.56 times 10 is 105.6. Think about that. Okay, so if you were to draw a ring on the ground, a circular ring that's 105.6 feet in diameter, Stonehenge would fit within a few inches within that ring. Now, the fact that they were using a consistent unit of measure is verified or confirmed by the fact that the distance, if you go around that ring,
Right.
and there's 30 uprights, which are most of the surveys and studies assume that there was originally 30 of those uprights, and several of the lintels, the horizontal lintels that cap those uprights, are still in place. Their average length is 10.56 feet. So think 10.56 times 10 gives you that ring.
Okay.
Okay, got that?
Got it.
Now what's 105.6 times 100?
105.6 times 100.
No, times 50, I'm sorry.
528. 5,280.
Our mile.
What the fuck?
Yeah. So what does that suggest? It doesn't prove, but it suggests that the builders of Stonehenge were using a system of measurement from which we derive our mile.
When do we think Stonehenge was built?
Well, it's Neolithic.
Yeah.
I mean, you're talking like, I think it's, what, 5,000 BC or somewhere like that, or maybe even earlier.
Yeah.
Yeah.
It's old.
At least Neolithic. I mean,
At least Neolithic.
Yeah.
So at least 4,500 to 5,000 years ago. At least, if not older.
Yeah.
Okay.
This suggests that our mile is that old. And they were using, if they had a mile of 5,280 feet, and you divide that by exactly 50, they now draw a ring on the ground, and that's the diameter of the sarsen stone circle at Stonehenge. And you divide that by 10, and that gives you the average spacing of the sarsen stone uprights. So,
Wow.
yeah, that's
bizarre.
now these are the kind of things we look at in the course that I do. Okay, so
Okay.
when we look at the Roman pace, which is almost Middle Eastern, right? It's, in Italy, not Middle Eastern, but it's Mediterranean. We'll call it Mediterranean. We're looking at roughly 2,000 years ago when the Roman pace was in Rome. It was well known that you had the city center, and the Roman mile was 1,000 paces out from the city center. Okay, so if we look at here, 1/1000th of the Roman mile is equal to 8 stades of 607.5 feet. Now that stade is where we get our term stadium from.
Yeah.
Oh,
Right?
really?
Yeah. Now a stadium was the distance around, so the British version of the stadium was called the Furlong. And we don't know how old the Furlong is, but it was apparently very ancient. Now, the only place that I know of where furlongs are still used today is where, Ben?
Racetracks.
Yeah,
right?
racetracks.
Oh, horse race tracks.
Yeah. But the furlong to the ancient Britons was 660 feet. 660 feet is 1/8 of a mile. Try it. 660 times 8 and see if you get 5,280.
5,280.
There you go. So a furlong was 1/8 of a mile. What's the origin of the furlong? I don't know. It's old. But see, that's more confirmation that the mile that we use today has ancient roots. Now here's something else that's interesting. We talked earlier about the Earth that we live on is an oblate spheroid.
Indeed.
And we know, as Ben was talking about, the equatorial diameter is 26 miles greater than the polar diameter.
Right.
Right? It varies from...
Now, why is that?
It's spinning.
Spinning.
Think about any spinning system. The centrifugal force is going to throw the mass of it towards the equator of the spin. And thank that God that it does, because otherwise conditions on the surface of the Earth would be so chaotic that it's highly doubtful that any kind of higher life ever could have evolved.
So if the Earth was a perfect sphere spinning, how would that disrupt the Earth? How would that disrupt everything, like the Earth's crust, the oceans?
Well, there would be, this equatorial bulge acts as a stabilizing flywheel.
Okay.
Right? And the Earth is not perfectly rigid. But it's interesting that you said if the Earth was a perfect sphere. If the Earth was a perfect sphere, what would be the measure of that sphere that would then have the same volume as the actual Earth? Well, the actual Earth varies from 7,926 miles at the equator, 7,900 miles at the polar diameter, so a difference of 26 miles. So what that means is that if you're standing at the equator, you're 13 miles farther away from this Earth's center than if you were standing at the North or South Pole.
Right.
And it also, you could think of it this way, if you traveled from the equator to one of the poles, you're going downhill 13 miles.
Oh my
Right?
God.
Right? Now let's think about this. Okay, so what would be, I'm glad you brought up the idea of the perfect sphere, because again, when we're talking about creation manifest in 3 dimensions, and the idea of sacred geometry is that behind the actual manifested 3-dimensional physical universe is this template, the template of geometry. In that template of geometry, you've got idealized numbers, okay? Now, the idealized number of the Earth would be what you just said. What would be the size of the Earth that was a perfect sphere, let's say, that had the same volume as the actual Earth?
Yes.
It would be 7,920 miles.
If we squished it into a perfect sphere.
If it was a perfect sphere,
Okay.
same volume as the actual Earth, 7,920. Get that number in
I'm
your
going
head.
to write that down. 7,920.
7,920.
Okay.
Got that number in your
Got
head? Okay. Let's go back to the furlong that we were talking about. Okay. Furlong, we agreed, was 1/8 of a mile, 660 feet. How many inches in 660 feet?
It's going to be the same number.
7920. What the fuck kind of sorcery is this? Whoa.
Now let's think of what we just saw here. Okay, we said the Earth, 7,920 miles, right? We've already determined that the mile is a human-derived unit of measurement based upon paces. You go and you walk out 1,000 paces on the surface of the Earth, and it's 5,280 feet.
Whoever developed the mile knew the circumference of the Earth.
Well, I'm not going to go make that claim, but there's something weird going on here. Now, picture, there's 2 things. When you say that the mile is 5,280 feet, each of those paces is 5.28 feet. So think you've got a ratio. The ratio is the length of the human pace to the human foot. That's ultimately the ratio of our mile. The pace to the foot, 5.28 feet, and 1,000 of those paces is our mile that we use today. Key number, that ratio, 5.28 feet, okay? You got to keep that in mind. And I know that, you have to work with these numbers for a while before they become embedded as part of your consciousness, part of your framework, your conceptual framework of reality. You just saw that the furlong, 7,920 inches. So think of this. You've got a furlong, 660 feet. Let's say you lay that out on the ground, and I have actually done this. Find a nice big open field or parking lot, lay out 660 feet. And then you mark out 1 inch, which, oh, by the way, is the width of your thumb originally, your digit. That's where the inch comes from, right? Put your thumb on a piece of paper, draw a hit on either side. You've got your inch. That's a derivation of the inch. So all of this is connecting human anatomy. You've got your inch. You've got your foot. You've got your pace. You've got your cubit, right? So now this is all linking the geometry to the human anatomy. So now here's the final thing that you want to get in your mind, the relationship. The furlong is to the inch as the Earth is to a mile. Got it?
Got it.
Okay, let's go further with this.
Oh,
Are you ready? I mean, this is we're just kind of like got one leg down into the rabbit hole. What I like to do is I like to get people that they put one leg in, then 2 legs, and while they're peering down, I come up behind them and I give them a push.
ooh. Let's go.
There you go. Okay, so in the book of Revelation, we were talking about the prophecy. there. St. John the Divine, he's met with the angel with the line of flax and the measuring reed, and he's got to measure the holy city and all of this. Then later on, it's describing his vision of the holy city. And it says, the city lieth foursquare, and the length and the height and the breadth of it are equal. What would that suggest to you? Foursquare, but that's got length, it's got height, and it's got breadth.
Cube.
A cube.
Okay.
12,000 furlongs. And the city lieth foursquare, and the length and the height and the breadth of it are equal 12,000 furlongs. Okay? How far is that? Put 12,000 in, and we know that a furlong is 660 feet. So go 12,000 furlongs.
7,920,000.
Now just look at the first four digits.
7920.
Does that look familiar?
Yes.
Yes. So now that's a lot of feet. Let's put that into some ratio.
That's the Earth.
Yeah. That's the measure of the earth times 1,000. Now let's put that, but that's feet. We just converted that to feet.
Got it. Okay. That's why it's so much.
But who can picture what's 7,920,000 feet? Let's convert that to miles.
Okay.
So you're going to divide by 5,280.
1,500.
1,500 miles. Now what's the ratio between that and the actual earth? So here's what, you've already got that in your calculator, right?
1,500, yep.
So that'll put 1,500 on top, divide by Earth, 7,920 on the bottom. Now you're going to flip that by hitting 1 over X, so that you put the big number on top and the small number on bottom.
Okay, I just did the divided. That gave me 0.18.
Okay, and then hit 1 over X.
Okay, 1 over X. 5.28. What in the fuck is this, Randall?
Okay, so
It's all connected.
yeah,
The implications that of this sacred geometry and some of the oldest structures that we found, basically it implies that they understood this long history.
yes, that's what I would read into it. Yes, that somewhere what this is showing, and I mean we've just scratched the surface of this.
Right.
I think what it's showing us is that somebody back whenever, and I would trace it right back into prehistory, had a very sophisticated knowledge of the architecture of creation. And they understood not only the spatial relationships, but the temporal relationships as well. And they were able to apply that in terms of sacred building, in terms of a technology. The wonder of it is, in some ways, is how we humans did not go the way of the woolly mammoths.
That is the wonder of it.
Yeah.
We did have a bottleneck. I mean, we know
Yeah.
there was definitely a bottleneck in both population and genetic diversity associated with the time frame of the Younger Dryas. It's kind of funny. There was a study done recently. Antonio Zamora's done some good little short YouTube videos on it if people are interested. But it is a study that shows that there was, across the world, all populations of humans almost everywhere, and these are disconnected, isolated groups, simultaneously went through a decrease in genetic diversity, and particularly in male populations, actually. And it's all associated with a period of time shortly after the onset of the Younger Dryas. And, of course, it's the study's authors don't make a connection to, the Younger Dryas period because it's still a debated topic, I guess, in what you'd call mainstream science. Mm-hmm. But they said that, well, perhaps it was just some sort of somehow simultaneous change in breeding and preference patterns between these isolated and different groups of people that resulted in this genetic diversity. But it also coincides with this extinction event, and turns out we're megafauna. I mean, I'm certainly megafauna.
Or 90% of the world's population got wiped out.
Well,
It's hard to say what percentage.
It wasn't that. There was a bottleneck in population and in just diversity, but I'm not sure if it was that much. But.
Yeah, it was probably, I mean, it could have been, I mean, we're just kind of at the beginning of piecing this together. I mean, clearly the human species was affected by these events. You don't have events that wipe out half the megafaunal species on Earth and not affect the other half of the megafaunal species that survived. It's not like half the species came through completely unscathed, but the severity and magnitude of those events completely exterminated half the other species.
Yeah.
Right? We know. Look at the how close the bison, the American bison, came to becoming extinct around the turn of the century. There was only a few hundred individuals.
Mm-hmm.
Now, we can go to the grocery store and buy bison burger, right? 1,000, 10,000 years from now, you could completely miss the fact that bison came this close to becoming extinct species. Because it's only, within a few generations, once we made up people decided that they wanted to salvage the species, it didn't take long for the species to recover. So, 10,000 or 12,000 or 13,000 years ago, a species may have come that close to extinction, but there was still enough numbers that the species within a few centuries could completely could recover. See, and it brings us to the question of, how drastically were humans affected?
Yeah. And I think there's parts of the world as well. It's not, as you were saying, Younger Dryas, although it was probably the most dramatic thing to happen to the planet in maybe 5 million years, it wasn't
5 million.
Yeah, it might have been the worst thing that's happened to the planet in 5 million, certainly from an extinction perspective. But it's not. There were parts of the planet that weren't as affected as badly affected as others. Certainly, North and South America were tremendously impacted with the species that went extinct. We see a similar thing in Europe, but you look at Africa or Australia, and there seems to have been much less impact. That's one of the Africa has a lot of megafauna, and you look at the what we estimate the age of lots of that megafauna is still going to be like 2 to 3 million years old. Like those species also lived through the Younger Dryas. Australia is somewhat similar.
Australia did undergo very severe mass extinction, but it was much earlier than the Younger Dryas. Yeah. Now, if you look at percentages, North and South America both experienced about a 75% reduction in megafaunal species. Yeah. So in other words, North America lost about 3/4 of the big animals. Think about the animals that used to be here in North America. 4 species of proboscideans. You had the sort of woolly mammoth, the Columbian mammoth, the imperial mammoth. You had mastodons. You had dire wolves. You had giant cave bears. You had huge moose. You had giant deer.
Armadillos.
What?
Armadillos.
Giant armadillos?
Size of a Volkswagen, bro.
Yeah. And you had and giant ground sloths. The list was up to like close to 100 species, right?
How do we know we had armadillos that big?
Because we found their remains. Yeah.
Go through Cincinnati Airport sometime.
Remains of these animals.
Cincinnati Airport, I went through there the other day. They actually had the skeletons. They had a dire wolf. They had a saber-toothed tiger. They had mastodons. They had one of the big elk, the giant elk. That were just like, my God.
Yeah. So
short-faced bear.
Now, okay, so North and South America both lost about 3/4 of their species. Eurasia lost a little more than a third. About 35% of species in Eurasia went extinct by the end of the Younger Dryas. Africa, 10 to 12%. So a lot of the big animals in Africa are the survivors of the Pleistocene. People don't realize that. When you start looking at rhinos and hippos and elephants and giraffes and all the rest of them. So clearly the cataclysm, the Younger Dryas cataclysm, was not uniform around the whole planet.
Right.
Now, one of the other things that I've noticed from going back into literature is that a lot of times, going back to the idea of how humans were affected, you had places where there was obvious settlements, had been there for centuries, and then all of a sudden they're abandoned. The usual assumption was, well, these people got up and migrated somewhere else. Problem is then the other places you find evidence of human occupation, and they're gone at the same time. You find quarries all over non-glaciated North American settlement camps and things like that, where people were living, working. You find the refuse pits, the middens, all of the things that was evidence that there was a fairly long period of occupation, and then all of a sudden it ends, and that termination coincides in many cases with the beginning of the Younger Dryas. And it's probably more a case, less a case that they got up and moved somewhere else, is that they didn't survive.
Right.
Like a quarry, where they're quarrying flint or stones for their spear points and things, are active for centuries, and then all of a sudden they're abandoned. Oh, well, they got up and moved somewhere else. Well, where'd they move to? But what's more likely is that, that particular social group died out, and that was the end of it.
How much debate is there over what caused the Younger Dryas, whether it be comets or solar ejections or all of the above?
Well, there's still debate. I'd say that there's at this point 160 odd papers peer reviewed that the vast majority are very much in favor of the cosmic impact / airburst theory.
Airburst meaning like it explodes when it hits the atmosphere.
Yeah, so it's initially I think people were thinking about thinking of it in terms of a single impact, but it very much seems like it was a series and potentially different periods of cosmic impacts and airbursts. Airbursts are also traumatic. I mean, there's actually been a few really good studies on sites that show cosmic impact. It's not related to the Younger Dryas, but Dr. Stephen Collins at Tel El Hammam basically discovered the source of the biblical Sodom and Gomorrah story. He did a digging on a site, and they've shown that site was actually subjected to a cosmic airburst, and it literally matches all the stories that's in the Bible, which you would probably attribute that to the wrath of God if you had happened to witness that from, a hill
right
a few kilometers away. But yeah, I mean, airbursts are bad as well.
The idea of the pole shifts.
Magnetic poles.
The magnetic pole shifted and the Earth did like a 90-degree tilt.
No, see, now a lot of these people that are speculating don't really even seem to understand the difference between the magnetic pole and the geographic pole. The geographic pole is the Earth's axis of rotation, right? The magnetic pole doesn't necessarily exactly coincide. In fact, it migrates. It doesn't coincide with the axis, the geographic pole, which is the axis of rotation. Those are two different things.
Yeah.
Now, I believe, I've looked deeply into that when I was first studying catastrophism, looking at the work of Velikovsky and Charles Hapgood and others. Charles Hapgood saw the catastrophic history of the Earth. He was trying to come up with an explanation. He came up with a relatively sophisticated model of crustal shift, not the whole mass of the planet, because he looked at the math
The
of
crust, right, exactly.
Right.
Earth crust displacement was his theory.
Right.
So it becomes disconnected from like the mantle?
Yes.
The asthenosphere, the plasticky kind of
Yes.
connection. You can think of the Earth as like the crust as being like the skin on an apple. That's like a relative thickness of it, right? But beneath that, we have varying degrees of like plasticity and connection. So it's like the tectonic plates are sliding around on the asthenosphere that has this plasticky kind of properties to it. And Hapgood proposed that could have been disconnected and shifted violently or suddenly, and then causing catastrophes.
He proposed that actually before continental drift was accepted by mainstream geophysics and geology.
Really?
Yes.
Yeah.
But of course, then when continental drift came along, this was a much slower process, where Hapgood was envisioning something much faster. Now, I'm not sure I'm 100% correct, but I'm pretty sure that Hapgood abandoned that idea eventually. He didn't abandon the idea of catastrophism, just the mechanism that caused catastrophism.
Yeah.
Now, I have it's very different. I think that back to the subject of isostatic compensation, you figure that, again, the geoid in equilibrium is spinning on its axis. So now, remember the 13-mile difference between
the equator and the Arctic.
That's the radius, yes.
Radius.
Yes. Okay.
Oh, never mind. Sorry.
Yeah, radius.
The radius. The diameter's double that, 26 miles. So so now you picture this. If you have a huge redistribution of surface mass, so let's say that the weight of the ice over North America depresses the area of North America under the thickest ice by a couple of thousand feet. Well, now it's not in equilibrium with its latitude anymore, is it? Because all of the surface of the Earth's crust, if it's in equilibrium, the northern latitudes are going to be miles closer to the Earth's center of mass than the equatorial. But now what happens if you change that distance by thousands of feet, or maybe even in the case of the ocean bottoms, a mile or two, right? Now it's not in equilibrium anymore. There's not that correlation between the latitude and the distance from the Earth's center of mass. Could that then lead to an accelerated plate tectonics where the planet is trying to regain that equilibrium? So in other words, if you've got large parts, the half of North America is depressed by 1,000, 2,000 feet, and then all of a sudden and I say all of a sudden in a geological sense over a few thousand years, it's moved away from the center of mass. Now it's the distance that it would want to be if it was at a much more southerly latitude. Does that make sense?
I think so.
It does. Yes,
I think so.
Yeah, so then the Earth, it's trying to re-seek equilibrium, which I think what you're saying is could that possibly cause a kind of a violent adjustment, which leads to volcanism,
a period of accelerated plate tectonics is how I would call it.
So it's
which
the
would
weight.
Be bad news.
You're saying it's the weight from
it's the mass,
or the mass of the ice sheets on top of.
Again, picture this oblate sphere. It's bulged out this way.
Right.
So at the equator, it's 13 miles, and it's happy there. Now, go 45 degrees north, halfway to the North Pole. Well, now it's 6.5 miles closer, right? Go even further. Now it might be 10 miles closer, right? Now all of a sudden, let's imagine that it shifts upward by thousands of feet. Now where it wants to be happy is going to be further south. It's going to want to be farther away from the Earth's center of gravity.
Got it. That makes sense.
Yeah.
And what would cause that to happen?
Melting glaciers.
Melting
rapidly.
glaciers.
Because you've got this huge redistribution of mass.
Right. Okay.
From off of the land surfaces into the ocean basins. And during the onset of a glacial age, you've got the opposite. You're drawing out trillions and trillions of tons of water from the ocean, piling it up on land, and now that weight is pushing the land down by perhaps several thousand feet. At the same time, you're removing that weight from the ocean basins, which is going to cause the ocean basins to want to rise. So picture glacial, interglacial. You've got water being extracted from the oceans, building up on the land surface. From glacial back to interglacial, this is all melting and going back into the ocean. So if you look at over a long period of time, hundreds of thousands of years, oscillation, glacial, interglacial, glacial, interglacial, the shape of the geoid is pulsating in response to that redistribution of surface mass.
Right.
Now, I think there's a possibility, and I'm not a geophysicist, but I think it would be a possibility that could introduce this disequilibrium that would cause the movement of the plates to try to shift. And once they start moving, the inertia of that movement, they're not going to necessarily stop, because clearly, like Hapgood was right, I think, when you look at orogenesis, mountain building. Have you ever been up in Canadian Rockies and look at these incredible overthrust faults? That's a future
Yeah, I'd love to
tour,
see that,
by the way, where you have slabs of rock, thousands of feet thick, thrust up over other, forming these mountain ranges. Well, okay, you can look at rates of erosion, and the higher you get material up, the faster the rate of erosion. The problem with mountains is this, that seems to be ignored, is that when you look at rates of erosion or downcutting, they're roughly, if mountains are being built by continental drift, and continental drift is a few centimeters or few inches per year, that would mean that they're moving, it's causing the plates to buckle and raise the mountains.
Right.
Well, the uplift of the mountains isn't going to be any faster than the lateral movement of the plates, But we've got mountains that are 10, 12, 13,000, 15,000 feet high. Yet when you look at the rates of downcutting and erosion, the rates of downcutting, of erosion, the eating away of the mountain masses being uplifted is roughly equal to the rate of uplift.
How'd they get up there?
How'd they get up there? Unless the rate of uplift was a whole lot faster.
Way faster.
Yeah.
Yep.
Interesting.
Yeah.
It's possible. I mean, I think places like Tiwanaku in the the Andes mountain range is like, that's a huge mystery about how the hell that whole plateau got up there and how it could have supported the amount of life that was required to create a city of that magnitude. There are some real clues to something potentially happening at a faster rate. I mean, I don't think it's like a day, like the Earth flipping over. There's too much inertia in the system and too much stability in the system for that type of thing. Just personally, again, I'm not a geophysicist either, but yeah, I am interested in the idea that something could have caused a fairly, at least geologically, quite rapid shift in the Earth's crust or at places like mountain ranges.
So I think we need to kind of I think we need to go back, take a kind of another look at the geological history of our planet within the context of catastrophism. Yeah. All of this, because now we can see things on a scale that our grandparents couldn't see. 50 years ago, 60, 70 years ago, we didn't have satellites where photography where you could now begin to see the scale of some of these events that have played out on our planet. So I try to bring in as much of that as possible. Then the crown of that is you go out in the field and you start seeing this stuff. And I'll tell you, even with all of the photography and the videos and the drone footage and everything, seeing that, until you get out in the field, you know, it just, that's when it hits you. You begin to realize, I'm like a microbe here.
Yeah.
I'm like a microbe. These things that have played out on the surface of this planet are in another realm altogether. So,
yeah, you can start to appreciate the literal, like one of the terms I've heard you use is like they call America was also known as the New World, and it literally is because it's built on the ruins of the old world, and you can get a sense for some of those processes when you start to see this. These catastrophes, and that's why I think catastrophism's and the evidence for it is such an important key that unlocks the possibility for a longer timeline and civilizations and things like this, is because it literally changed the surface of the Earth. It's between the flooding, the fires, the sea level rise and falls, it changes the surface of the Earth. And this is the video we put together.
What is this, the Devil's Canyon?
Okay, this is drone footage from
actually
none other than...
I did put this
Ben Van Kerkwyk.
Yeah. Am I okay to
go? I sent it to you for this very reason.
Yeah, okay, but I want to make sure that it's understood. This is Ben's work here.
Yes,
I did.
This is one of the places we visited. This was a canyon that was probably cut in a matter of a week or two, and
cut by
hit play
by one of the great floods. Now let's take a look at this.
Yeah, this was basically an outflow down to the Snake River, right?
And what you're seeing here is not a canyon produced over millions of years, but a canyon produced over a few weeks by a flow that probably would have been close to 50 million cubic feet per second or greater. And
so this entire canyon was rushing with water.
Yes.
For a short period of time. And it's been dry since. It's like...
Yeah. So now this is in the channel scale. So this was on one of our tours. And you'll see... as we pan around, and again, a lot of this is not going to be, it's not going to necessarily speak to somebody until you've been trained to read the language.
Right.
But now you can see here, there's the group. There's some outcrop boulders that were left in the aftermath of the great flood flows.
Those things on the left?
Yeah.
Yeah.
There you can see our vans.
How
deep is that from the very middle of it to the top?
The deepest part, what it would be 800 feet maybe?
Maybe 600 to 800 feet.
Oh my God. It was I mean, was it overflowing this at one point? It probably.
Well, it started with
an overflow, and then it cut down.
Mm-hmm. And here's what you call a cataract, this bowl-shaped feature. Now, this entire landscape that you see here was completely submerged. This Palouse Falls is that's the whole remnant, but you can see it's cutting its own little cataract there. But the cataract produced by the big flood was this big round thing that you're seeing all in here. This is one of our regular places to visit, and it's mind-boggling in scale. So this is one of your great features here. This is called Potholes Cataract. Picture out here, this is like a turbulent moving sea.
Okay.
The entire width of the scene here. It's probably close to 200 feet deep. It's choked with thousands of icebergs. It's moving towards the viewer. And this is a ridge, and behind you can't see here, it drops down into the Columbia Valley. This water is pouring over this ridge, and these walls here are about 400 feet high. Think about this. If you have floodwaters coming through, ripping up stuff, excavating, eroding, well, that's half of it. The other half of the equation is that material is transported and it has to be deposited somewhere. So you learn to correlate both of those. What kind of rock is ripped up from here and where does it end up?
Right.
But you're going to see West Bar here, which is pretty amazing. We're coming around. This is West Bar. You're going to see it now.
So are there giant rocks here that came from somewhere else?
Oh, yeah.
Glacial erratics, yeah. There's rocks and huge chunks of granite that probably came from Canada that are deposited out on this giant, like a strewn floodplain. And where these coulees ended out, it's just these boulder fields that go for hundreds of square miles of just huge chunks of basalt, even some granite that probably came from a long way away. And then you get these big erratics where, like Haystack Rock and things like that are just these giant boulders that were deposited.
Now, I want you to look here at the surface of this 3 mile long, 200 or 300 foot boulder bar has giant current ripples on it. Now, the height of these current ripples varies between 30 and 50 feet. The height of up to a 5-story building. And that's how we know without any doubt at all. There we go. Look at these. These are the kind of current ripples. I mean, you'll see them walking along a sandbar on a creek, except that these current ripples are gigantic. Like I said,
Isn't this also seen in the Sahara?
Well, you have sand dunes in the Sahara, and they're being blown by wind, not water, and they're dynamic. They're constantly moving. These are not moving. These are pretty much like they were when they were deposited 13 or 14,000 years ago, when this gravel bar, it's actually a boulder bar.
That's what you see when the tide comes out of the beach.
Yeah, that's right.
Scale and variance, right? It's a great example of it. Like the same sort of phenomena at work in small scale as it did with this.
Right.
You can imagine this current of water coming around the inside of this bend, just giant current of water that left these current ripples.
Mm-hmm.
Wow. These 50-foot high current ripples that are there now.
It's almost impossible to comprehend that.
Wait till you see it firsthand, Danny.
Yeah.
You got to put on your bucket list that you want to go on one of these tours.
I'm coming. Yeah, no, haven't people pointed out specifically, I think it might have been Jimmy who pointed out that those things are near the reshot structure. Those water ripples.
That was me.
That was you?
Yeah.
Oh,
yes.
Okay. Maybe Jimmy got it from you, because I think I heard Jimmy say it too.
Well, Jimmy has been arguing that the reshot structure is Atlantis.
Exactly, yeah.
I don't agree with that. Now,
Right. I remember you were here last time. You said it's Azores.
I think that the most if it existed, I think the most likely place that's the most consistent in the details of Plato's two dialogues is the Azores as a remnant. Those islands are the tops of mountains whose bottoms are part of a plateau that about which there is a lot of evidence that it has subsided by a substantial amount since the last ice age. Jimmy has been arguing that the reshot structure is Atlantis.
Exactly, yeah.
I don't agree with that. Now,
Right. I remember you were here last time. You said it's Azores.
I think that the most if it existed, I think the most likely place that's the most consistent in the details of Plato's two dialogues is the Azores as a remnant. Those islands are the tops of mountains whose bottoms are part of a plateau that about which there is a lot of evidence that it has subsided by a substantial amount since the last ice age. And I do I've got like 9-hour lecture that I do on that. It's a pretty solid case.
I watched it. It's phenomenal. I watched it after our last podcast.
Oh, excellent. Okay.
Wasn't there a recent voyage that went out to the Azores to look at this?
I don't know.
We were talking about this. I thought
James Cameron I thought he was supposed to look at. I haven't heard anything about that since it happened. I mean, but I wasn't involved in it. But a lot of the science on this,
a seamount dive or something.
Could have been. Yeah, I don't know.
It's unfortunate that a lot of the actual science looking into the mid-Atlantic ridge submergence sort of ceased, in the 70s and 80s?
Yeah.
Most of the real science, once Atlantis became a dirty word,
right?
They kind of stopped looking at it, but I think it...
Oh, yeah, like for example, one of the seamounts was named the Atlantis seamount. In the literature and everything, and I've got the old from the 50s, 60s, 70s, and then we get closer to now, the same seamount has been renamed the Atlantic seamount.
Really?
Yeah.
That's bizarre.
Well, I mean, to try to, don't want to have that connection.
To try to get rid of that
the Atlantis thing.
That woo-woo connection to Atlantis.
Right. But what I try to show in my dissertation on it is that it isn't woo-woo.
Right.
What's woo-woo about it? I mean, if you start talking about, whatever, crystal spaceships or whatever, yeah. But if you stick to whatever Plato actually says, which is what I do, I pretty much break Plato's two dialogues down and go, what did he actually say? Now, what is geology, geography, oceanography, and so forth, botany and genetics, what does all that say now in the context of what Plato said? And that's where I come up with, that to me, Azores fits the bill. But I'm not saying the Azores was Atlantis. What I'm saying is that if Atlantis was real, of all the places that have been named as potential sites for Atlantis, I think the Azores is the most consistent with Plato.
And where did Plato, he got his information from Socrates?
Solon.
Okay.
Well, actually, from descendants of Solon. In the Socratic form, it was Critias, who was like a great-grandson of Dropidas, who I think, if I'm recalling the succession, he got the original story from Solon, who got it from the Egyptian priests, who gave him the date, which was 9,000 years. In their sacred registers is Sauntius was the name of the priest.
And that would have been when compared to now?
Well, Solon's trip to Egypt occurred about 600 BC. So if you had 9,000 years to 600 BC, which would have been 2,600 years ago, what's 9,000 plus 2,600? 11,600, which is precisely the end of the Younger Dryas, which precisely coincides with what's called meltwater pulse 1b, where there was a massive melting of the great ice sheets, pouring water into the oceans, causing the oceans to rapidly rise. Coincidence? Maybe. But what if it's not coincidence? All the pieces fit.
This is the stuff that I know you cover in your lecture series on it. But once the glaciers melt, you have isostatic rebound of the Earth's crust, which is the lifting up, like the all that weight of ice on the top of the globe here is going to come off it. So I think I love the beach ball analogy.
Yeah.
It goes up the mid-Atlantic ridge, which is where the Azores is located, is essentially like, think of it as like a hinge joint in the crustal plate on the planet. So imagine,
right.
So imagine if the land over here is going up, and what's it going to do? It's going to pull that apart. So you're going to have submergence of the landmass at that mid-Atlantic ridge at the same time. Yeah, it's going to go down.
It's isostatic compensation.
Yeah,
because the Earth is constantly trying to make equilibrium. So if one place goes up, someplace else has to go down, and vice versa. That's the geoid. It's trying to constantly adjust itself to fit the mathematical geoid, which is the perfect distribution of mass given the mass of the Earth, its orbital speed, it's rotational velocity rather, which is what causes that bulge around the equator. So during the Ice Age, you had this enormous buildup of ice on the planetary surface, on the land. All of that weight, which is billions of trillions of tons, is taken out of the oceans. So like Brent said, the beach ball analogy, if you take a beach ball and you press it this way, it bulges this way, right? If you, Danny, get up and go over and sit down on that cushion, what happens? Isostatic depression. When you get your ass up off that cushion, you'll have isostatic uplift or isostatic compensation. It'll come back up.
Right.
Right? I told this to Joe Rogan when I was explaining to him, and I said, Joe, you probably didn't realize that right at this moment, your ass is causing isostatic depression of the cushion on your chair. He probably doesn't remember that. But I did say that to him.